Isotopes. Atoms in the periodic table are identified and arranged according to the number of protons. Neutral atoms or elements have the same number of electrons. Neutron numbers can differ for the same atom or element. The periodic table lists the average mass, calculated according to percentage composition in nature. Atoms with the same atomic number but different mass numbers have different numbers of neutrons. Let's have a look at the simplest, most straightforward atom, and that is hydrogen. Now you will see there are three isotopes of hydrogen. The atomic number, or the number of protons, is here at the bottom, and the mass number at the top. This isotope has no neutrons. The mass number and the atomic number are identical. In this isotope, there is one neutron, increasing the mass number to 2. And here there are 2 neutrons, the mass number is 3. Now, to determine the actual mass number on the periodic table, the percentage occurrence also has to be considered. So you will find that the actual mass in the periodic table is not 2, which is the average of 1 plus 2 plus 3, but it is 1.0079. Now there is a way of determining the mass of individual isotopes. Often you are asked a question to determine the mass of a particular isotope X. Now then you have to remember X is the unknown element, Z is the atomic number, which is the number of protons, the thumbprint, the mass number is A, and this is how the unknown element is represented conventionally. Here's the example of hydrogen again. You will see that with one neutron, hydrogen is also called deuterium. With 2 neutrons, it's called tritium. Uranium has 2 isotopes, and its actual mass is closer to this isotope, so clearly the abundance of this isotope is greater. Let's just look at the periodic table now. There you can see what I've been saying about hydrogen. It is 1.0078, and uranium at the bottom is 238.076, so it's closer to uranium 238. We're now going to do some calculations of other elements on the periodic table, but before we do that, let's have a look and see if you just understand using carbon as an example. We've got carbon 14 and carbon 11. You will notice they both have the same protons, 6. The element's neutral, so the number of electrons is 6. Subtracting the atomic number from the mass number, this isotope has 8 neutrons, and this isotope will have 5. Let's consider boron, which is quite a simple element to start with. Now, boron has an atomic number of 5. There are 2 isotopes of boron. Get boron 10 and boron 11. Both have the same atomic number. The actual mass of boron 10 is 10.0129. The actual mass of 11 is 11.0093. This is measured in atomic mass units. Percentage abundance is 19.91% and 80.89%. Now, if you multiply the actual mass by the percentage abundance, you get the contribution of that particular isotope. So we must multiply 10 by 19.91 divided by 100, which will give us a value of 1.9935. Then we have to multiply this isotope, 0.0093 by 80.89 divided by 100. And the value we get there is 8.8173. If we add these together, we will get the value which is printed on the periodic table. Let me show you. There you can see boron, element number 5. The actual mass is 10.21. So you add up the contributions of the different elements. Let's look at chlorine. Chlorine has an atomic number of 17. There's one isotope is chlorine 35 and the other isotope is chlorine 37. The actual mass of chlorine 35 is 34.969 and the actual mass of chlorine 37 is 36.9666. Percentage abundances 75.78% and 24.22%. Once again, multiplying out as shown, which you must do yourselves, should give you the value of 35.45 atomic mass units. Let's look at an element that has 3 isotopes. Silicon. Atomic number 14, we get silicon 28, 29, and 30. The abundances here, silicon 28 is by far the greatest abundance, but let's look at its actual mass first. 37.9769, 28.9765, 29.9738, multiplied by 92.23% and 4.68% and 3.09% respectively. Remember to divide by 100 when you're multiplying a percentage. And if your calculation is correct, when you add up the 3 contributions, your value should be 28.085 atomic mass units, which will correlate with the value on the periodic table. Then there's just one other way that this sort of question may be asked. You may be given the mass of the different isotopes and asked to work back and give the percentage abundance of one of them. For instance, we look at silver. One of the isotopes has a mass of 106.90509 atomic mass units. The other one has 108.9047 atomic mass units. The value on the periodic table is 107.8682 atomic mass units, and you are asked to determine the percentage abundance of this lighter of the 2 isotopes. What you then do is you say, okay, let the percentage be X multiplied by 106.90509 plus 1 minus X multiplied by 108.9047 is equal to 107.8682 atomic mass units. And they're all in atomic mass units. And you have to remember we're talking about 100% is complete abundance, and we're looking at a fraction of that. So ideally I should have said X and 100 minus X. But let's make it 1 minus X here and multiply by 100 later to make the calculations and the number of figures easier. You can do it either way, it's your choice. You should get a value here of 1.9996x equals to 1.0365, which is equal to 0.518. Multiply by 100 and you get the percentage abundance of the lightest isotope is 51.8%. Now, just to finish this whole thing off, I have set a quiz. I have put it onto the My Tutor platform so you can complete it there and hand in your answers. But I would just like you to look at it quickly so you're aware that it's there. Look at it here. You are asked to give the correct answer to the real mass of the unknown element X. There are 3 isotopes. You're given the mass of each and the abundance of each. You select the correct one. You can only do that if you calculate it. And then the second question likewise, a different unknown element X, use the abundance and the mass. Remember, the abundance is given as a percentage. And submit your answers on the My Tutor platform, where you'll immediately be notified if you are correct.